On va commencer avec 15 secondes. Ah non, ça y est. Il est 17h pétante. Merci à tous d'être venus. Donc, je suis très heureux de vous présenter quelqu'un que vous connaissez sûrement d'ailleurs, par ses nombreuses, pas forcément personnellement, mais par ses œuvres, qui est Edward Lee, donc qui est professeur à Berkeley dans le Centre Electrical Engineering and Computer Science, qui est totalement illustre et personnellement une de mes grandes références, qui a créé une grande partie de l'industrie californienne, en particulier ce qui concerne la CAO de circuits électroniques. Cadence, Synopsys, c'est un peu des startups de Berkeley, mais il y en a plein d'autres. Et donc, Edward Lee est spécialiste des systèmes temps réel embarqués, de leur simulation, de leur conception, de leur programmation. Et il est très connu comme auteur du principal et chef, c'est le bon mot, du système ptolémique qui existe depuis 20 ans. C'est un projet sur la très longue durée. Berkeley et en particulier EECS savent faire des projets sur les très longues durées, ce qui n'est pas forcément courant aux États-Unis. Donc Ptolémie est vraiment une référence dans le monde de la simulation de systèmes et surtout dans le monde qui va intéresser mon enseignement de cette année, qui est le monde du multiparadigme, de comment faire cohabiter des paradigmes assez différents les uns des autres, qui ont toujours été assez éloignés les uns des autres dans la littérature, et qui se mettent à cohabiter, et c'est pas simple. Et cette histoire n'est pas finie, loin de là. Mais je pense que vous allez voir ça à l'œuvre. Donc il a écrit 9 livres, dont un absolument merveilleux, dont on va voir des extraits, je pense, dans l'exposé, qui est un livre animé, c'est-à-dire que vous pouvez l'acheter sous forme papier, vous pouvez l'utiliser sous forme PDF, et tous les exemples fonctionnent. Donc vous cliquez sur les exemples et le web se met à les faire fonctionner, et c'est assez magique et c'est extrêmement utile. Alors, il est également directeur du centre multi-universitaire qui s'appelle TerraSwarm, qui vise à peupler la Terre de bestioles non biologiques. Il faut reconnaître qu'en ce moment, on parle beaucoup de big data. Big data, c'est un grand sujet, mais les gens n'ont pas réalisé que le sujet d'après, c'est big animals, big swarms, big little devices everywhere, et qu'il y aura bientôt beaucoup plus d'ordinateurs que d'humains, qui vont tous se parler, et ils vont aussi faire des choses intéressantes, entre autres. Ils ne vont pas forcément faire que ça. Et donc ça, c'est évidemment des choses qui intéressent très directement mon enseignement. Alors, donc, nous connaissons parce que Edward Lee est venu à Sophia Antipolis passer une sabbatique, il est venu d'ailleurs d'autres fois, et moi je suis passé aussi à Berkeley. Et donc il est aussi directeur d'un grand labo qui s'appelle Chess. C'est pas un labo, c'est une grande coopération industrielle avec des financements non français entre des industriels très prestigieux des États-Unis et l'université de Berkeley. Donc, il a fait des tas d'autres choses, en particulier dans l'enseignement, où il a eu des prix pour la qualité de son enseignement, et on va pouvoir constater ça. Et voilà, je vais terminer là-dessus. Donc, l'exposé durera à peu près 1 heure, à peu près. Si vous avez des questions urgentes pour l'exposé, n'hésitez pas, mais sinon, on aura du temps pour les questions après. L'amphi étant de toute façon fermé au public à 19h. Mais 19h, c'est dans 2 heures. Donc, amusons-nous bien, apprenons beaucoup de choses. Enjoy.
Merci Gérard. Bonsoir, messieurs, dames. I'm not going to torture you with my French. I think you will be very relieved that I'm going to switch to English now, but I try. Thanks for coming. Much appreciated. My agenda today is to try to convince you of what I think is really quite an intellectual opportunity and a challenge. And it centers around this concept of cyber-physical systems, which is a term that was coined a few years ago, 2006 or so, by Helen Gill at the National Science Foundation. And I think at the time, many people were a little bit suspicious since, basically the National Science Foundation is about funding research that it was really just a way of renaming existing research in order to bring more money into the topics that the people in the community were working on. But what I want to convince you of today is that it's not at all the case, and that in fact it is a profoundly interesting technical challenge. And so that's my agenda. So cyber-physical systems refers to the orchestration of networked computational resources with physical systems. So The interesting thing about them is always that they combine some kind of physical dynamics that is, in some sense, either controlled by computers or autonomous on its own. And then they include sensing devices that are providing input to the computing devices, and the computing devices are interacting with each other over networks. And you might say, well, this is not a new problem. Of course it's not a new problem. All modern aircraft, all modern cars are in fact cyber-physical systems. And in fact, I have to say I started working on cyber-physical systems in 1978 when I was writing assembly code for Intel 8-bit microcontrollers to control robots that were all air pressure driven. So it was all about opening valves, opening and closing valves. And it was for manipulating blood samples in a clinical pathology lab. So these robots would do things like reach out, grab a test tube from a carousel, drop it in a centrifuge, spin the centrifuge for some period of time, then pick up the test tubes, put them back in the carousel, move them on to the optical reader that would measure the levels of the layers in the test tube and so forth. And so if I was doing this in 1978, how can this possibly be a new problem? So what I'd like to try to convince you of today is that really this problem has at its heart a collision of two very long intellectual traditions that are actually not very compatible on the face of it. So the first intellectual tradition is the one of what I might call traditional engineering. So this is electrical engineering, mechanical engineering, civil engineering, where there's a very long history, at least 200 to 300 years, of people developing models for systems and ways of designing systems, ways of imagining their behavior, understanding their behavior, controlling their behavior, okay? For example, one of the most commonly used tools in that space is ordinary differential equations, which you use to describe the dynamics of a system, okay? A much more recent history is the history of computer science, maybe 60 to 80 years old, roughly, or maybe 100 years, depending on how far back you want to go. And in that discipline, the very notion of computation also talks about dynamics. But it talks about a very, very different kind of dynamics. In computer science, dynamics is sequences of transformations of data. And that kind of dynamics is not at all the same kind of dynamics that is described by ordinary differential equations. And in my opinion, there's an enormous opportunity to take what we've learned over the last decades in these fields and develop new models that can work well with the conjunction of these two traditions. So that's really my agenda today, and that's what I'd like to talk about. So I'm dividing my talk into three parts. So the first part is going to be about engineering models for cyber-physical systems. The second part is going to be about time, which turns out to be one of the key concepts where today there is an enormous amount of friction between these two traditions. And the third part of my talk will be about some promising approaches that we're pursuing at Berkeley. And the goal of that part isn't to convince you that what we're doing at Berkeley is wonderful. It's to convince you that there are potentially interesting solutions to this problem. So that's my goal in the third part of the talk. So let me start with engineering models for cyber-physical systems. So the first thing I'd like to do is zero in on the word models. And here I'd like to rely on some really wonderful analysis that has been done by Solomon Gulam. His writing on the role of modeling is really very insightful, and I think well worth reading for anyone who works with models, which is pretty much anyone in the sciences, engineering, and mathematics. Solomon Gulam, one of his key theses was that it's really important for people to make a clear distinction between the model and the thing being modeled. And unfortunately, in practice, people don't often keep that distinction very clear. the two concepts get confused, and they easily get confused. And he had a wonderful phrase for underscoring the importance of this distinction when he said, "You will never strike oil by drilling through the map." Now, an interesting thing about this phrase is that in no way does this diminish the value of a map. It's not meant to be disparaging of models. It's just that you have to understand that the model serves a different role than the thing being modeled, and that it has different properties than the thing being modeled. But both are very valuable. And in fact, models, in my opinion, are absolutely essential to engineering and science. In fact, those subjects are really all about models. That's at the core of these subjects. So models are valuable. Now, the second point that I'd like to make is one that I learned from Hermann Kopetz, and he didn't actually originate this concept. In fact, I later discovered that this concept is actually written into the policies of the nuclear power industry for defining the safety of nuclear power plants. But nevertheless, I learned it from Hermann Kopetz. I learned it when I stumbled upon him at a breakfast at a conference in Grenoble. I was thoroughly jet lagged. I dragged myself out of bed, went downstairs to get a cup of coffee. There he was. I sat down with him and started talking. And he told me this concept, and it really changed my thinking about things. So the key idea here is that he asserted that many of the predictive properties that we assert about systems, things like determinism or timeliness or reliability or safety, these are not, in fact, properties of systems at all. They're not properties of the systems that get deployed. They're properties of models of the system. And we can make definitive statements about models. So when people talk, for example, about formally verifying a system, that phrase bothers me because if it's a physical system, you can't formally verify it. But a model you can formally verify. You can make proofs about models. You can prove safety conditions about models. And of course, those proofs are useful as long as your models have reasonably good fidelity. They actually describe well the behavior of the physical system. But useful models will almost never perfectly describe the physical system. They will always approximate it. So it's really important whenever we make definitive statements about systems, whenever we assert properties, to realize that we're asserting properties of models and not properties of the deployed system. Now, let me focus on determinism, because determinism, I think, is an extremely valuable property of models. And it's one that I think many people discard it too easily because they say, well, the world is unpredictable and there's lots of non-determinism in the world. Therefore, our models should be non-deterministic because that's the reality of the world. But I think history actually shows quite the opposite. I think that much of the technology revolution of the 20th century is actually firmly founded on deterministic models. So one of these deterministic models is synchronous digital logic. So the way that synchronous digital logic works is you have circuits which consist of logic gates like AND gates, OR gates, adders, multiplexers, and so on. These circuits are actually fairly messy devices. The transistors are not trivial. They're moving around seas of electrons and highly random behavior under the hood, okay? But the synchronous digital logic abstraction is one that allows us to consider these gates not as physical systems with all their imperfections, but as simply as logical operations. And the way that it does that is simply by defining a step that is made where inputs are presented to the circuit at a time corresponding to a clock, and then the results of the circuit are latched at the end of the clock period. And all of the messiness of the circuit occurs between those two clock periods. And as long as your clock is not too fast, your circuit with very high fidelity will behave as if those gates were perfect. It essentially The circuits can be made to behave as if the gates are absolutely perfect. So, I mean, to emphasize the perfection of this, you can build a digital circuit that will perform some arithmetic function 1 billion times a second that will work perfectly for years. And in fact, we rely on such devices all the time today. I do not believe that the billion transistor chips that we make today would really be possible to design without this abstraction, okay? But this is a model. This is the physical system. Will the physical system always behave like this? Well, no, you have no assurance of that. How will this physical system behave while it's being crushed? How will it behave if the temperature rises, if there's a fire and the temperature rises above some threshold? There's no assurance that it's going to conform with this model. Nevertheless, the model is useful because we're able to build systems where the model is highly faithful to their behavior, okay? Another example of a deterministic model, which I think underlies the 20th century revolution in information technology, is that of single-threaded imperative programs. So these are programs that just proceed through a well-defined sequence of steps transforming data, okay, one after another. And you can build programs that, again, are enormously complex, millions of lines of code, and yet have very predictable behavior. And the physical realization, of course, is the same one as the synchronous digital logic. In fact, this is just another layer of abstraction on top of the synchronous digital logic, okay? But it's an exceedingly useful model because it is deterministic. The fact is you provide the inputs to a piece of single-threaded imperative program, and you provide some initial state, the state of the memory, and the results of executing this code are well-defined. They're unique and well-defined. And I don't believe that much of the information technology revolution would have happened if this were not, in fact, a deterministic model. If you want to go to concurrent systems, I mentioned single-threaded, unfortunately, the prevailing practice, the dominant practice in computing, is to give up determinism. And the cost of doing that is enormous. One of the exceptions is the synchronous languages, which originate here in France and are a wonderful intellectual coup because they showed definitively that concurrency is not equivalent to non-determinism. They're not the same thing at all. And in fact, I've had computer scientists define concurrency in terms of non-determinism. They're not the same thing at all. You can have concurrent deterministic systems, and the synchronous languages show this very elegantly. Now, these models that I've given are all kind of in this information technology space. What about the traditional engineering models? Well, in traditional engineering, in mechanical engineering, civil engineering, electrical engineering, people describe the behavior of messy mechanical devices like these using models which are in fact deterministic, mostly. Ordinary differential equations. This is here is a representation of Newton's second law, F equals ma. Extremely useful tool for defining the dynamics of systems. Completely deterministic, okay? And many of the control systems that we rely on today, say flying aircraft and so forth, depend on our ability to analyze mechanical systems using these kinds of deterministic models. Now, the problem for cyber-physical systems, I would like to assert, is that we don't actually have deterministic models for cyber-physical systems. As soon as we take these deterministic models for computing and we combine them with these deterministic models for the physical world, the combination is non-deterministic. This is the problem we have to fix. And if we fix this problem, we're going to be able to do an awful lot more with our technology. So let me elaborate on this problem. So here's a simple schematic of how a cyber-physical system might be constructed. You've got some physical plant. So a physical plant is just some device you're trying to control, okay? An aircraft, for example. And you have actuators which are coming from computers, are being controlled by computers. So the computers are issuing commands that are having an effect on the physical world, and the physical plant is going to react to that effect, right? If you turn the rudder on an aircraft, the aircraft is going to react in a way that you can understand using differential equations, okay? You also have sensors attached to the physical plant, which are also attached to computational platforms, which are going to read that data, do some computation, and maybe communicate over networks to other computational platforms, okay? So in this kind of a system, we have an overall closed-loop behavior, okay? The question is, what is that closed-loop behavior, and how do we go about designing it? And one of the immediate problems that we run up against is that the behavior of the physical plant is extremely dependent on the timing of the actions in the computational platform. When it does things matters a lot. The dynamics of the physical plant is described in terms of its evolution, the evolution of its state in time. But the dynamics of the computational platform is not defined that way at all. It's defined as a sequence of step-by-step changes in state. And so we have an abstraction for the behavior of the computational platform, and we have an abstraction for the physical plant, and they're not really compatible. So let me try to prove to you that they're not, in fact, compatible. So here's a very small segment of code. This happens to be a C program, and this C program describes the typical way that in software, ultimately, you control timing, okay? You might say, well, no, actually, I control timing because I use a real-time operating system and I set priorities. Well, this is what the real-time operating system will do in order to control timing, okay? So under the hood, pretty much every real-time system out there controls timing in some manner similar to this. Now, what is this program doing? Well, I'm not going to torture you with a little programming exercise, but in general, it just does some setup in this main procedure, and then it enters a while loop that it would like to execute for some period of time, and then it would like to proceed and do something else. Now, this is a C program, and it's a model, in fact, and it's a model for which we have faithful implementations. We can have microprocessors that will, with high confidence, execute this program exactly as specified, okay? However, what does the program specify? Well, the way that it controls timing is doing what I call, I use the phrase with my students, the Harry Potter style of design, where you look up in an arcane, dusty book called the spec sheet for this microprocessor that you're going to use, and you find the magic incantations like sys tick int register that are going to make something happen, and you issue those incantations, sys tick int register, and something happens. And what happens? Well, in this case, if you actually look under the hood and figure out what these magic incantations are doing, ultimately what they're doing is extremely simple from the software perspective. They're just writing data values to memory locations. That's all they do. They write a constant into a memory location. Now, it just so happens that on the board that this program will run, there's a piece of hardware that's looking for that memory location, that memory address, and it's going to grab the data value and stick it in a register that's going to control an external device called a timer, okay? And that timer is then going to raise an interrupt request periodically because of the values that you wrote into this memory mapped register. Now, does the program say that? Actually, the program doesn't say any of that, okay? The program is a model. It's written in a modeling language, C, and what it says, what the model says, is that the program writes values to these memory locations. Why these memory locations? Who knows? The program doesn't know. The model doesn't say. It's just a side effect of the hardware implementation that you actually get a timing behavior from this system. The model doesn't specify the timing behavior. The timing behavior emerges when you take that model and implement it on a physical system. All right? In effect, you're not really working with a model, or rather, you're working with a very incomplete model. Your model is failing to express a critical property of your system. And that critical property is emerging not from a model, so it's not a designed property, it's emerging from an accident of implementation. Some piece of hardware actually is what gives you this behavior. Now, what are the consequences of this? Well, if you need precise control over timing, which you often do in cyber-physical systems, designs are brittle. Brittle means that small changes can have big effects. And this is a common problem. System behavior only emerges at system integration time. This is particularly problematic for expensive, complex systems. Consider an aircraft, for example. Okay? There's many subcontractors. They're developing subsystems. And you're going to discover behavior only after you've gotten shipment of all those devices and you put it all together and find out what it does. That's not really very good engineering practice. And in fact, a lot of projects fail because properties emerge at system integration time that were completely unpredictable because they weren't a consequence of the models that were, or they weren't even represented in the models that were being used. One other consequence, which is really particularly telling, is that manufacturers stockpile the parts to suffice for the complete production run of a product. So Airbus tells me that, that they purchase microprocessors for the entire production run of a commercial aircraft when they finalize the design of that aircraft. Now, a production run for a commercial aircraft is often 50 years. They store these microprocessors that they buy in liquid nitrogen to try to slow down the natural diffusion processes in the silicon so that the processors don't degrade, so that in 50 years they can use a 50-year-old microprocessor. And this is the only way they can get assurance that the behavior of the system will be the same 50 years from now as what they designed today. To me, this is a failure of engineering because we know how to make devices. We know how to make models that can execute on a variety of hardware perfectly correctly, right? C programs execute on a wide variety of microprocessors correctly. So why is it that it's not enough to execute these programs correctly? It's because these programs don't actually express what the correctness criteria that are needed. That's the essential reason. The program is the model we're working with. It doesn't express the properties you need. Therefore, correctly executing it is not enough. Manufacturers can't leverage improvements in the hardware. This is, by the way, even a problem, even in much more modest scenarios. Often, manufacturers have to choose their devices that they're going to use well in advance of shipping the product. That often means that when the product rolls out the door, it's using technology that's already 2 or 3 years obsolete. And at the rate that things change here, if you didn't have to use obsolete parts at that point, you could tremendously reduce weight, reduce power consumption, improve reliability, et cetera. Any change you make in your system because it's brittle requires retesting and recertification. Very expensive process, often. And designs get over-provisioned. You have to be very conservative about your designs because you're not really sure what are the properties that are going to emerge at system integration time, and so you way over-design the systems. Now, I feel like we've gotten away with this for many years now, and the reason that cyber-physical systems exist and are reliable is because Moore's law has allowed us to be sloppy about the engineering. It doesn't hurt us that much to over-design, over-provision, et cetera. But to me, this is profoundly problematic and certainly transitory. Moore's law will not continue forever, And I believe that we can do much more if we simply use better engineering practices for these systems. So I'd like to talk about this issue of correctness. So when you have a model, we can define a notion of what it means for an implementation to be faithful to the model. The implementation has to do what the model says, okay? We call that correctness. If the implementation does what the model says it should do, the implementation is correct. So the fact is, with all widely used programming languages, the notion of a correct execution of the program has nothing to do with how long it takes to do anything. The timing of this is irrelevant. So a consequence is that programmers have to step outside the programming abstractions if they want to specify timing behavior. So in effect, programmers are working without maps. Now, it's not that computer science has completely ignored timing. That's far from it. In fact, timing has been a critical property. My own colleague, Dave Patterson, made a huge impact on the world of computer architecture by establishing that, in fact, quantitative measurements of timing should be used to guide the design of microprocessors. But the key thing here is that the timing is a performance metric. It is not a correctness criterion. And there's a big difference between a performance metric and a correctness criterion, because correctness criterion has to do with the fidelity of the model, and a performance criterion has to do with cost. Very different issues. Now, what do I mean by a correctness criterion? Well, here's another little snippet of C code. And if you're a clever programmer, you can follow that, in fact, it is true that line 8 in this program will never execute in any correct execution of this program. Now, in C, you have to be a little bit careful to be able to make such a definitive assertion. That is a definitive assertion. Line 8 never executes, okay? It requires a careful choice of a data type, and it requires some assumptions because C is a slightly sloppy language, and we have to separately ensure that there's no other thread or interrupt service routine that will mess with the stack and things like that. But modern languages provide these kinds of guarantees by construction, so you don't really need that. But in any case, under these assumptions, we can make that assertion that line 8 will never execute. Now, a consequence of that is that we can actually develop absolute confidence in the software. Absolute. Again, I'm talking about a model, right? We have absolute confidence in the software. Line 8 does not execute in any correct execution of this program. So the only excuse for executing line 8 is a hardware failure. That doesn't mean it can't happen. Hardware failures happen. Or you could get an alpha particle that flips a bit in your program counter that causes line 8 to execute. So it can happen in a physical realization that line 8 will execute. But in the model, it does not execute. And that's a very valuable property. We can, in fact, prove safety conditions using such assertions about programs. That's what I mean about a correctness criterion. We have no way of making such correctness assertions with regard to the timing of programs. It's simply not there in the abstractions that we use, and it's not available. Now, you could say, well, maybe the technology is incapable of doing it. But actually, that's not the case. The technology is perfectly capable of doing it. Every modern computer is built on top of synchronous digital logic, and synchronous digital logic is very good at doing things with very precise, very repeatable timing. So we could, in fact, have control over timing and high-fidelity implementations. We could have models with timing and high-fidelity implementations. But we chose not to. We chose abstractions for software that don't say anything about timing. And that was a choice. It's an engineering choice to build these abstractions. So the first challenge is, can we change programming models so that correct execution of the program always delivers the same temporal behavior? Of course, we always have to talk about the fidelity of the models, so with high precision, at the boundaries that they're interacting with the physical world. We actually only care about the timing at the interaction with the physical world. We don't really care within the program. So we need determinate cyber-physical system models and high-fidelity implementations of those. So challenge number 2 is that changing abstractions is difficult. People are stubborn. They don't like to be told that they need to use a new abstraction. This is just a fact about people. So that's a problem. We need open minds, and I don't know of any other way to solve the problem unless we're willing to accept some possibly new abstractions. Okay, time. I very much focused on time here because it is a tremendous point of friction between the cyber and the physical worlds today in cyber-physical systems. Now, I want to emphasize that with over-design, we can actually manage to control time and get good cyber-physical systems. We have lots of examples out there that are over-engineered, right? So there's plenty of margin. Unfortunately, the amount of margin you need to reliably control time keeps getting bigger because computer scientists keep getting cleverer and cleverer about exploiting the fact that timing is irrelevant to correctness. And so you need bigger margins today than you needed back in 1978. When I was writing assembly code on an 8-bit microcontroller, I could actually control the timing by just counting the number of instructions before something happened. You can't do that anymore with microprocessors. Far from it. Your estimates will be way off on the timing. And moreover, they will not be predictable. So let me talk about time, because in the context of cyber-physical systems, the very notion of time is subtle. In the traditional engineering disciplines, electrical engineering, mechanical engineering, et cetera, people widely use this variable t to represent time. It's a real number, and it's assumed to be universally available. Everywhere in your system, you've got the same value of t. In cyber-physical systems, however, that's not the case. You don't have, in fact, access to this variable t. In fact, actually, you don't really in any physical system either. The variable t is not something that you can read and manipulate. You can have measurements of it on your computational platforms, but these measurements will be imperfect. And if you don't take into account the imperfections of this measurement, you will have allowed a sneaky introduction of non-determinism into the system, and you might undermine the critical properties of your model. So we need models of time that, in fact, are going to allow us to control time in a deterministic way in the models. There are naive answers out there. On the physical side of the cyber-physical world, it's this variable t. On the cyber side of the cyber-physical world, it's just a double precision floating point number, which is actually floating point numbers are a pretty poor choice for a representation for time. They have properties, for example, that the precision of your measurement of time depends on the magnitude. Well, why should that be? The magnitude, of course, depends on what you choose as your time origin. So if you choose your time origin to be 4,000 years ago when God made the Earth, you're going to get a different answer than if you choose the Big Bang, and a different answer than if you choose January 1st, 1970, like the Unix world did. These are going to give you actually completely different precisions. Why should that arbitrary choice affect precision? It's also true that addition of floating point numbers is not associative. If you have 3 numbers, A, B, and C, the result of adding them together will depend on the order in which you add them. And that's unfortunate because if you want a clean semantic notion of simultaneity, 2 things occur at the same time, which I believe is necessary for determinism, you're going to have to be very careful about how you do arithmetic on these numbers because you will otherwise allow a sneaky introduction of non-determinism into your models. So this is not a very good choice for a model of time, yet it is the most widely used choice in the cyber world. Now, these are sort of negative comments. I'd like to make a positive comment. There's a really wonderful thing happening in the technological world right now, which is clock synchronization. And I am actually extremely excited to see what the effect that this is going to have, because historically, clock synchronization has had a huge impact on the world when there have been very big advances in clock synchronization. Okay? So in the 1500s, the Gregorian calendar synchronized clocks around the world to precisions of roughly plus or minus 1 day. So you could get agreement with 2 clocks on opposite sides of the planet within plus or minus 1 day about what the time was. Okay? A 5 to 6 orders of magnitude improvement happened in the 1800s, with primarily driven by the railroads. Okay? The railroads defined time zones, and they realized quite high precision clocks, which they put into the railroad stations, that synchronized clocks on the order of seconds across the planet. Okay? You could actually get synchronized clocks on the order of seconds. And of course, one of the main motivations for the railroads was, of course, to be able to efficiently manage shared resources like tracks, for example. Today, clocks around the world are getting synchronized to under microsecond precisions. And I predict that in 5 to 10 years, every device that's on a network will have a clock that is synchronized with every other device that is on a network to precisions of under a microsecond. So it's another 6 orders of magnitude improvement in clock synchronization across the planet. Now, how is this happening? Well, the first major development here that drives this, of course, is GPS. GPS gives you access to a clock anywhere on the planet that will give you precisions on the order of 100 nanoseconds, so 1/10 of a microsecond. 2 clocks on opposite sides of the planet can agree on the time of day to within 100 nanoseconds. But GPS isn't available indoors. It's not pervasive through networks. So what's happening in networks these days is that clock synchronization is making its way into all of the networks that we use in our day-to-day lives. So the start of this was the introduction of this standard, IEEE standard called 1588, which was developed primarily by a fellow named John Eidson. He was the sort of the leading driver behind the development of this standard. And it started appearing as a routine addition to the hardware that you use in your PCs to connect to wired networks around 2007. Today, this standard is supported in pretty much all new wired networking hardware. It's getting integrated into the networks, into the backbone as well, okay? So clocks are getting synchronized using this standard. And as of 2007, National Semiconductor, which was one of the first to introduce such a device, claimed that they could get clocks on a local area network to agree about the current time of day to within about 8 nanoseconds. So these are devices separated by kilometers of cable, and at the speed of light, this is about a nanosecond. So it's quite a good concurrence. Today, they're getting better precisions than this, even sub-nanosecond precisions. In fact, one of the more extreme examples of the use of this technology comes from CERN on a project that's associated with the Large Hadron Collider. Now, the Large Hadron Collider, you may know, is about 27 kilometers in circumference, so it's about 10 kilometers in diameter, roughly. And the White Rabbit project at CERN was able to synchronize clocks here with clocks here, 10 kilometers away, to within precisions of about 80 picoseconds, which at the speed of light is this far, okay, roughly. That's an extraordinary concurrence of an agreement on the current time of day. This project, by the way, was the one where a graduate student used this technology to discover the flaw in the physics experiment that was showing that neutrinos were traveling faster than the speed of light a year ago last summer. He used this technology to discover that flaw. Now, I personally think this is game-changing. And once we can rely on the fact that clocks across the planet are synchronized to this level of precision, it's going to change a lot of the way we design a lot of systems and a lot of services that also have, scales that are large. I believe that we can improve energy efficiency. We can accomplish coordination even without communication. Obviously, the White Rabbit project is doing that. If this is the speed of light and the clocks, if this is 80 picoseconds at the speed of light and you've got clocks 10 kilometers apart that are agreeing on the current time of day, it's not because they're communicating that concurrence, right? So you can do coordination without communication if you have synchronized clocks. I believe you can improve security, you can improve resource management, you can improve determinism, but I'll skip these in the interest of time because I could go on for the remaining, I could go on until 7 p.m. talking about this, but you would get tired of hearing about it. So the third challenge, in summary for this section, is that we need to develop a model of time that's consistent with the realities of time measurement. It needs to be able to take advantage of clock synchronization, but it needs to be aware that clock synchronization is never perfect so that it doesn't allow in some sneaky form of non-determinism, okay? So we need a semantics of time. Okay, so for the final segment of my presentation, I'd like to talk about some of the promising approaches that we're pursuing at Berkeley. So since I just talked about models of time, I'd like to give you a sense of what we could do with models of time that might be interesting. So we've been working with a notion that we call superdense time, which turns out to have some pretty useful properties. So in particular, what superdense time allows us to do is to talk about the temporal dynamics of systems that have very different character from one another. So in particular, if software, sequence of transformations of data, doesn't have the same kind of temporal dynamics as, say, a mechanical arm. So the question is, can we have a model of time that will talk well about these kind of mixtures? We need this model of time to be able to embrace continuously evolving state in time, right? So physical dynamics. We need it to be able to also embrace discretely evolving state in time. So these are physical events, for example, collisions of physical devices. If you want to model the collisions as discrete phenomena, which is a useful way to model things, then you need your model of time to be able to embrace that discreteness of the collision. Of course, central to cyber-physical systems is software controllers. And so these are going to have discrete behaviors in that a software controller will issue a command as an event. It's an instantaneous phenomenon to issue that command. And then that command will have an effect on the physical world. And it's useful to have models that exhibit that ability to have this interaction between a discrete behavior and a continuous behavior. And signal processing systems, of course, have this character as well. The model of time also needs to be able to embrace sequentially evolving state, where there really is no passage of time included in the model. So let me zero in on one of these to illustrate what we could do. In particular, I'm going to zero in on physical events like collisions. And the reason is that these are very easy to visualize, and you can see, hopefully you can see immediately why it's useful to come up with a better model of time than the traditional ones, okay? So consider a physical system like this one. This is Newton's cradle, and this is a simulation of Newton's cradle. And of course, it's a simulation of a perfect Newton's cradle, okay? So the collisions are perfectly inelastic. There's no loss of energy. There's no, over time, the balls in the middle don't move, okay? Nevertheless, it's a useful model of a physical dynamics. In fact, the goal of someone who's designing one of these toys is to come as close as possible to the model that describes this ideal behavior, right? That is the goal of an implementation of this system. So having this model, this idealized model, is useful. Now, I'd like you to consider the momentum of the second ball, which doesn't move at all. So what is its momentum? Well, its momentum must be 0. But somehow, the momentum of the first ball is transferred to the fifth ball. And the only way I can see that that could happen is if it goes through the second ball, right? It's got to go through the second ball. So the momentum of the second ball can't possibly be 0. So we could model, using classical mechanics, the momentum of the second ball this way. First of all, the momentum we just model as a function from the reals to the reals. And we just say that the momentum is 0 almost everywhere, except at the instant of the collision, when it is non-zero. Now, this works fine in classical mechanics because the motion of the ball will be proportional to the integral of the momentum. And this function integrates to 0. So the ball doesn't move. So this works in classical mechanics. But what happens when we try to come up with a discrete representation of this? We'd like to present this phenomenon, for example, to a microcontroller. Okay? It's measuring momentum. How are we going to do that? Well, we could try sampling it at regular intervals of time, but we're going to find that, well, unless we choose this particular time, we're going to get that the momentum is always 0, which is a highly inaccurate model, right? If we include this time in our sampling, then we're going to get a representation of this signal that is indistinguishable from one that will actually cause the ball to move. In fact, there is no way to tell whether that sampling comes from a signal that will not move the ball or a signal that will move the ball. So in fact, there is no sampling of this classical mechanics representation of this signal that will unambiguously represent this discrete event. So the superdense time model is a very simple modification of this classical model. The momentum now is modeled as a function of the reals cross naturals. So the naturals are just 0, 1, 2, 3, 4, 5, et cetera. Okay? And we simply declare the momentum of the ball to be 0 almost everywhere, except at one particular point. Okay? But I want you to notice carefully what this point is. It's the time of the collision and only one of the values of this second argument. So if we look at the momentum of the ball at the time of the collision, the momentum of the ball at the time of the collision is first 0, then non-zero, then 0 again. So it instantly moves from 0 to non-zero and back to 0, okay? And now I can actually represent this sequence of values using samples. I can discretize the signal unambiguously and come up with a representation that unambiguously represents the phenomena that the ball does not in fact move, and this event was genuinely discrete. Okay? So this is what I mean by elaborating on models of time in such a way that we can improve things a bit. So the flaws with the conventional model that this solves are discretizing the momentum by sampling yields a signal that's indistinguishable from a continuous signal. But in addition, momentum is not conserved because at the time of the collision, all three of the balls in the middle will have a non-zero momentum. And the total momentum in the system will sum to 3 times the momentum of the ball that collided with it, which is a little bit weird. Seems to violate some basic laws of physics. So the superdense time model solves this problem, as well as the discretization problem. It also provides a very nice property, which is now the signals can be piecewise continuous. The classical model, the signal is not continuous at the point of the collision. But with this new model, the signals can be, in fact, continuous from the left and continuous from the right at the time of the collision, even though there's a discontinuity in the signal at that point. Okay? This turns out to be a very nice practical consequence because you can use conventional numerical solvers for ordinary differential equations more easily because of this piecewise continuity property. So you can read more about this in this free textbook that was edited by Claudius Ptolemaeus, who came out of retirement after 2,000 years to edit this book at this web page, and it has a description of this model of time and some of the consequences of it. I'd like to just briefly talk about PRET machines. And so PRET is an acronym that I particularly like because it has at least 5 different meanings. But let me first tell you, before I tell you the meanings, what the goal of this project is. So microprocessors that we use today are built around a concept called an instruction set architecture, which is a concept that was originally developed by IBM in the 1960s. IBM developed this concept of an instruction set architecture in order to solve a real business problem, which is that they were having trouble selling customers new upgraded machines because the new upgraded machines wouldn't run the old software, okay? So they would have to rewrite the software if they bought a new machine. So they said, well, let's make it so that the software will run correctly on multiple machines over generations. So they developed this idea of an instruction set architecture, which is an abstraction of what the processor does. Now, in the 1960s, computers were used primarily for running payrolls, determining the winnings on horse racing tracks, things like that. And there's some time criticality to those things. You know, determining winnings in horse races, you can't take forever to do that, or your customers get very angry. But these are not cyber-physical systems. And so timing didn't matter, it mattered only as a performance metric. And so the choices that they made in designing instruction set architectures didn't include any way to control timing. Those are still the choices that we're stuck with today. Machines, microprocessors are designed still in very much the same way, much more elaborated, of course, with better technology. But the basic principles of the abstractions are identical. So the PRET machine project is an attempt to go back and re-examine those assumptions and say, well, can we in fact design instruction set architectures that give us very precise control over timing and still allow programs to run correctly over multiple generations? Okay? So the project, the acronym stands for Precision Time Processors, or Predictable Repeatable Timing, or Performance with Repeatable Timing. Of course, it's the French word for ready, and it's a Dutch word for fun. So all 5 meanings I like. But the key idea here is really to design instruction sets that give us precise control over timing, repeatable behavior, enabling the use of a model where correct execution means doing something at a precise time. Now, the fact is, we know we can design such machines. In fact, in 1978, when I was programming these robots for the clinical pathology lab, I was using a PRET machine. I could count cycles because I could control timing completely precisely. It wasn't in the instruction set architecture, but it just happened that the implementation had perfectly controllable timing. The bottom line is that we've actually been able to show that you can achieve control over timing without giving up performance. And that's the thing that we really needed to try to convince people of, because you can certainly do it if you're willing to give up performance. The key is whether you can do it without giving up performance. And we've got demonstrations that, in fact, you can. But again, in the interest of time, I'm not going to give you the details on that story. And I'll move on to the final topic of promising approaches, which has to do more with programming models. So here, I'd like to just give you a brief sense of how we might approach designing systems that are large in scale, that take advantage of clock synchronization, that have deterministic models, despite the fact that they're executing highly concurrently and physically distributed, and that give us precise control over timing so that the interactions with the physical world are part of the model, okay? Those are a lot of objectives at once. And they're objectives that are not currently addressed in software technology for the most part, okay? So in order, I should apologize in advance because this story tends to be a little hard to grasp, okay? And I think I blame myself for that. I haven't found yet the magical way to explain it clearly. I've tried a few things. I'm going to give you my best attempt so far to explaining this, okay? And hopefully at least give you a sense of what becomes possible. One of the reasons that it's hard to explain is that because this model assumes that clock synchronization is not perfect, we have multiple timelines to work with. So it becomes treacherous to use words like, when X happens, we want to do Y. Well, what do you mean by when? According to which timeline are you talking? But it gets worse because we have in this model physical measurements of physical time, so clocks that are being synchronized imperfectly, but we also have a logical notion of time operating in these models. And this logical time gives us yet another timeline to work with, and there's a relationship between that timeline and the physical timelines. And I have had situations where even within the team that's working on this project, we start arguing about things and we just go in circles because we have trouble with the language. And the language has a way of talking about time that assumes time is uniform everywhere. And so it's a little difficult to find the language to talk about this. But nevertheless, I'm going to try. So here's the scenario. We've got a physical plant. It's got actuators that we can control by computer. So this is this box represents a piece of software that is going to probably, by writing to memory mapped registers, cause something to happen in the physical world, okay? The physical plant is going to react, and sensors are going to be triggered, and the software, this box represents a piece of software that is able to read that sensor, again, probably by reading a memory mapped register. So it's just reading a memory location from the perspective of software. In this scenario, I've assumed that we've got 3 computers labeled Platform 1, Platform 2, and Platform 3. They're communicating over some network, and they're performing some computation on the sensor data, and they're sending messages that are eventually causing some actuation, okay? So once again, we've got an overall closed-loop dynamics, and we're interested in being able to control, model, design that closed-loop dynamics, okay? So the boxes we call actors, and they represent computations. So an actor has inputs. These are inputs. It has outputs, and it reacts to inputs, performs some computation, and produces outputs. The messages carry timestamps, and this is the first timeline that we're introducing here, and it's a logical timeline. The timestamps are a logical concept, and they simply represent an ordering in which we would like computations to occur, okay? They're just talking about ordering. So logical timestamps define the interleaving. So in particular, if I get a message from Platform 1 carrying a timestamp, and I get another message from Platform 2 carrying another timestamp, I want this computation to react to those 2 messages in timestamp order, okay? It should react to the one with the earlier timestamp first, then react to the one with the later timestamp, and it would be an incorrect execution to react in the opposite order, okay? Now, second step, we assume that the 3 platforms have clocks that are synchronized. So these are measuring physical time, okay? They're synchronized, and we can bound the error on the synchronization. So now, all of a sudden, I've gone from 1 timeline to 4, okay? Because there's 4 timelines, 1 on each of the platforms. We're assuming some concurrence. So we've got bounds on the relationship between 3 of these timelines. So far, the 4th timeline has no relationship to the 3, okay? Not yet. But But the clocks we can use to give a global meaning to timestamps. How do we do that? Well, we want to process messages in timestamp order. So in order to do that using synchronized clocks, we have to somehow bind that fourth timeline into the first three. The way we do that is at the sensors and the actuators. So a sensor reads data from the physical world and produces time-stamped values. The timestamp here will represent the time as measured on this platform at which the measurement of the physical world is taken. Okay? So that's how I'm going to get timestamps in the first place, is by just, when a sensor takes a measurement, using the local clock, I timestamp that measurement and then launch it into my computation. And henceforth, I will treat that timestamp as a logical object. So it's now in the fourth timeline, and it will be used to process events in timestamp order. At the actuators, we do the converse, where we treat the timestamp as a deadline and also as a command to the actuator. So when we deliver a timestamped event to an actuator, we interpret that to mean that we would like the actuator to take an action in the physical world at a physical time specified by that timestamp. Okay? So it becomes a deadline because if we deliver the event, the timestamped value to the actuator after physical time has passed the timestamp, then the actuator can't possibly take its action at that specified time. Okay? So this gives us a model. We need one more thing, because if you notice, nothing in here suggests that timestamps are altered along this path from the sensor to the actuator. So if the sensor produces a timestamped value, I do some computation, create a value with perhaps the same timestamp, send that over to the network, do some computation, produce a value again with the same timestamp, send that timestamped value to the actuator, I'm almost certainly going to be late, right? Because the timestamp was the physical time at which this actuator made the measurement, and if that time has passed, right? It's passed on this platform. If you have reasonable concurrence in the clock synchronization, it has probably passed on this platform as well. So we have to specify latencies by manipulating timestamps. So in this model, we include components that will specify an increment to a timestamp. We call it a delay. It's a logical delay. And it specifies that this is simply a component that takes a timestamped value and produces a value with a greater timestamp on its output. And that, in effect, now specifies the latency between the sensor and the actuator. Now think about the overall dynamics. If I have perfect clock synchronization, okay, and I deliver events to actuators on time, and the actuator uses the timestamp to affect the physical world at that physical time, then I have perfectly deterministic closed-loop behavior. Okay? I can completely analyze the dynamics of the system, the overall closed-loop system, even though it's including physical and computational components in it. Okay? So that's the model that we want to use. Now, how can we use this model? Well, to use this model effectively, we have to make some assumptions. Okay? So first, the first key constraint is we have to ensure that events, timestamped values, are processed in timestamp order. That's pretty challenging because you can have streams of timestamped values coming from different sources. This stream here is coming from a remote platform, and this one here is coming from a local computation. How do we know whether we can process the local timestamped value? We have to somehow be sure that we're not later going to get something coming in over the network that is going to have an earlier timestamp. Okay? That's going to be key to processing events in timestamp order and preserving the determinism of the model. So we call that the safe to process analysis, because if we have a time-stamped event here, we need to determine when it is safe for that actuator to react to that event, okay? So we can do that, it turns out, if we make some assumptions about the physical realization of the system. The first assumption, we assume a bound on the network delay. You can see immediately that if we don't assume a bound on the network delay, we're dead in the water, right? Because if the transport time is arbitrarily large here, we can never be sure that we will not later receive an earlier time-stamped event from that remote device, right? So we have to assume a network-bounded delay. We also have to assume that the sensor, if a sensor timestamps a value, that there's a bound on the time before the software sees it, okay? We call that the sensor delay. And we have to assume a bound on the clock error, and we use this specified latency, and then there's a rather simple formula for the safe-to-process analysis. This formula can be statically computed. It's part of the compiled program, and it'll determine, in fact, when it is safe to process a local event by just looking at the local clock. So it's safe to process this event when the local clock exceeds a pre-computed value. As soon as the local clock exceeds its pre-computed value, I can process this event, and I'm guaranteed to process events in timestamp order as long as all my assumptions are satisfied. The network delay is bounded, the sensor delay is bounded, and the clock synchronization error is bounded, okay? All models require assumptions in order to have faithful implementations, right? All of them. So this is too many assumptions? Well, again, let me remind you, right? The value of models. This is a model. We have to make assumptions about an implementation. Even the synchronous digital logic model, perfectly deterministic. But you still have to make assumptions. You can't clock the circuit at an arbitrarily high rate. There's a bound on how high you can clock a circuit implementation in order to be able to have a faithful realization of that model, okay? That's true of all models for which you have faithful implementations. There's going to be assumptions. And by the way, these assumptions that I made are all routinely made today in safety-critical systems. If you go to Airbus, you're going to find that they assume a bounded network latency. In fact, they design their network to try to ensure that it will behave that way, because if they don't have a bound on the network latency, they're going to have a really hard time controlling that plane. They also synchronize clocks. They use time-triggered networks, but they do it by broadcasting a clock over the network, which is a rather more crude technique than the ones that are used in these clock synchronization protocols. So these assumptions are there anyway in the systems that we deploy today. So I don't think this is too many assumptions. We can, in fact, have a deterministic model. Now, the model as I've described it so far only guarantees that events are processed in timestamp order. It doesn't guarantee that events will be delivered to actuators on time. That's actually a separate question. And I thought, since the first PhD thesis on this TIDES model, which was written by Yang Zhao, I assumed, because the model was very expressive, I assumed that the question of whether events would be delivered to actuators on time was undecidable. It seemed obvious to me that it was. And one of my students, Christos Stergio, just recently, as part of his PhD thesis, proved me wrong. I love it when students prove me wrong. It's just extremely gratifying. And he showed that, in fact, for a very large subset of these models, the schedulability problem is actually decidable. Again, under a number of assumptions. One of the assumptions, by the way, is that each chunk of computation has a bounded execution time, but whether it does is undecidable. So there's still an undecidability problem, but nevertheless, this is a really nice result. Now, just to help validate this, this model, Google, a whole bunch of people at Google, this is the author list for this paper, independently developed a very similar idea and published it in OSDI in 2012. They're using it to control database accesses on a distributed database that's distributed across data centers. They synchronize clocks across these data centers, and they timestamp all the queries going into the database, all the updates and all the requests for data. They timestamp them, and they process these in timestamp order in a distributed fashion using essentially the same technique. So that we like it when people reinvent our stuff because it helps validate the idea. So it's a change in philosophy. The conventional approach, you specify the functionality you'd like, you design a processor architecture, and the behavior emerges from the implementation. That's how people do it today. The TIDES approach is you specify the temporal behavior, and every correct execution will give you that temporal behavior. So now you just have to ensure that the execution is correct. You don't have to ensure, you don't have to discover the behavior from the implementation. If it's correct, it will be what you designed. So it offers a deterministic model of computation for distributed real-time systems. So the challenge that this one, so there's another challenge that I could talk about, which is how we actually build these models. And we have promising approaches, but I think everyone's going to get tired, so I'll skip that topic as well and just summarize that the four big challenges that I've talked about to some degree, although the fourth one virtually not at all, is that we need determinate cyber-physical system models. We need open minds about languages and tools. We need a semantics of time. And the final one is that we need a discipline of model engineering. And this TIDES programming model is just a starting point because engineering these systems requires a lot of tools and techniques that are not yet developed. Having the programming model is a barest beginning of a starting point. So I'd like to close with acknowledgments for the people who have made tremendous contributions to my thinking about these topics, which is the people in this list, and I've probably omitted some, but, and I'd like to thank you very much for your kind attention.
Merci Edward pour ce talk assez fantastique. Alors d'abord, je voudrais donner quelques nouvelles pour ça. Vous avez compris, si vous avez lu le programme de mon cours de cette année, qu'on va parler des temps variés. Donc ça, c'est le premier exposé du cours. C'est pas moi qui le fais, c'est très bien. Comme il y a d'autres choses beaucoup dans le travail d'Edward Lee et de ses collègues, il y a des cours cette année qui se feront à partir de son travail. Et par exemple, il y a un cours sur la coopération de modèles de temps où j'utiliserai brutalement Ptolémée. Ça vous permettra aussi de voir ce système assez fantastique à l'œuvre et de voir l'élégance avec laquelle tout y est fait, que ce soit les dessins, la sémantique et la publication. Et le fait que cette publication, c'est un livre animé comme pour les enfants. Et ça, c'est vraiment très bien parce que ça marche, tout ça, vous pouvez le voir. La deuxième nouvelle, c'est qu'il y a maintenant une liste de distribution, une liste pour le cours. Vous pouvez cliquer sur liste de diffusion et dans ce cas-là, vous vous inscrivez à cette liste dans laquelle je vous communiquerai pas mal d'informations pour l'année. Pour ceux des internautes qui n'ont pas vu l'exposé en direct mais qui vont regarder ce film, c'est pareil, vous pouvez cliquer là-dessus. Et par exemple, je me permettrai de recevoir des messages. Alors, tournez cette fois votre souris avant de poser des questions, je veux dire poser des vraies bonnes questions, qui ne font pas qu'il y ait 4 pages de long. Et certaines, je me permettrai de les transmettre, surtout si elles le concernent à Edward, sans le surcharger, parce qu'il a déjà pas mal de travail, pour avoir des réponses. Mais de toute façon, on va revoir des choses comme ça. Il y a beaucoup de choses qu'il ne nous a pas racontées, par exemple qu'on sait faire des horloges atomiques qui font un petit centimètre cube, ce qui je ne savais pas du tout, et que ces horloges atomiques peuvent être mises dans des systèmes, et ce qui permet de voir. François Anceau nous fera, dans un exposé du cours, quelque chose sur la synchronisation à grande échelle, très précise d'horloge sur une puce, sur une de ces puces modernes qui sont très grandes, ou ailleurs. Donc on verra, parce que je vais aussi vous parler des protocoles de synchronisation dans le deuxième cours ici. Je vous rappelle aussi qu'il y a 3 cours qui se feront à Sophia Antipolis sur un sujet différent. Je vais essayer de les avoir en streaming. On va voir si c'est possible ou pas. Mais en attendant, on va passer aux questions directement. Aux questions. Vous pouvez parler en français si vous voulez, on saura traduire, ou en anglais, c'est encore plus simple.